Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on January 9th, 2026, just 4 days ago. It reveals a framework where an 8 billion parameter model achieves about 95% accuracy on hard math problems, outperforming GPT-5. The paper is titled PaCoRe, Learning to Scale Test Time Compute with Parallel Coordinated Reasoning. And as we'll see later, the way it decouples reasoning from context limits is really promising. And for those interested in the implementation, the authors have shared their code on GitHub. Figure 1 visualizes this performance breakthrough. The left panel tracks accuracy on the HMMT 2025 math benchmark as test time compute increases. The blue line, representing PaCoRe 8b, climbs steadily as the model uses more compute, eventually crossing the purple dashed line to surpass GPT-5. Moving to the right panel for coding tasks, we see a crucial difference. The gray baseline model flatlines because it cannot leverage extra compute, whereas PaCoRe, shown in blue, continues to improve significantly. Well, Figure 1 just showed the performance, and now Figure 2 details the inference pipeline that makes it possible. It starts with the problem instance on the left. The system feeds this into the central coordinated reasoning block, where the model generates many parallel reasoning trajectories to explore different solutions at once. Then, the compaction function distills these diverse thoughts into concise messages. These messages loop back to guide the next round, allowing the model to refine its answer iteratively without running out of context. So, having seen the pipeline in Figure 2, Table 1 now presents the headline results across 7 major benchmarks. The upper section lists large frontier models like GPT-5 and QN3, while the lower section tracks PaCoRe 8b scaling from low to high intensity. Look at the HMMT 2025 column. The high compute variant achieves 94.5% accuracy, edging out GPT-5's 93.2%. This is remarkable because it trades massive compute, nearly 1.8 million tokens per problem for intelligence, allowing a much smaller model to compete at the top. The apex column shows a similar trend, where the baseline scored 0, but the high compute strategy pushed that to 2.3%. While Table 1 showed the final results, Figure 4 breaks down the components driving that success. The left chart compares parallel scaling in blue against sequential scaling in orange, showing that parallel trajectories utilize compute far more effectively. Then, the panels on the right demonstrate why message passing is essential. In the bottom right subplot, the orange line reveals that without compaction, input size explodes to hit the red context limit line. Because the model runs out of context space, looking at the top right, its accuracy collapses, while the blue line scales robustly. Alright, Figure 4 proved the design works, and now Figure 5 reveals how these skills emerge during training. On the left, the graph tracks the frequency of cross-checking words, which the model uses to cite other reasoning branches. This behavior steadily increases for both math and code tasks, meaning the model is actively learning to coordinate rather than work in isolation. Then, the bar chart on the right measures something called emergent correctness. This tracks how often the model finds the right answer even when every single input message from the previous round was wrong. The rising bars confirm that the model isn't just voting. It is learning to synthesize valid solutions from flawed evidence. Wrapping up, 2 takeaways stand out. PaCoRe successfully decouples reasoning volume from context limits by using parallel exploration, and this allows a compact 8 billion parameter model to outperform giants like GPT-5. It suggests the future of AI might rely as much on inference time architecture as on model size. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.